Lesson number 10, modeling real-world data with linear functions. In recent years, there has been a growing interest in problem-solving and mathematical modeling. In 1975, for example, the Conference Board of the Mathematical Sciences put out a recommendation that we should integrate and incorporate problem-solving and mathematical modeling in all strands of school math. In 1989, the National Council of Teachers of Mathematics did the same with their documents called the standards, the Curriculum and Evaluation Standards. They also stressed the incorporation of mathematical modeling and problem solving in all areas of school mathematics, in particular in algebra. When you think of a model, you might be thinking of something physical, tangible, concrete. For example, a child will make play toys like a plane or a boat out of paper. Those are model airplanes, we can say. Or artists and sculptors, they often make small-scale models of their ultimate work of art. Or even architects always make scale models of the buildings or structures that they will eventually build. But models are not always concrete, tangible, or physical. Demographers use demographic models to predict the growth of populations. Economists use economic models. Those are not concrete and tangible. They are based very often on mathematical principles. So a mathematical model is something that can be an equation, for example, like we're going to see today, a linear equation or a quadratic equation or other equations. And the point of a model is to mimic, to approximate, to resemble the events or the data or the phenomenon that we take out of the real world and we analyze. So we're going to do that several times, 2 times. In the first case, we're going to collect the data ourselves. In the other case, we will get it from input that we've already have in our calculator. So in a nutshell, think of 2 worlds. On the left, as you see in the diagram, you have the real world. In the real world, we have events, phenomena, patterns, problems, data, questions. On the right, you have the mathematical world. In the mathematical world, we have concepts and processes and theorems and theories and axioms and postulates and equations. These are the 2 worlds that we've been dealing with. In the second graphic, you see that we start with a problem situation that we take out of the real world. We analyze it and we simplify it. We therefore make a mathematical model for it. That process from the problem to the model is called mathematizing or mathematization. Once we have the model, which in our case will be equations, we go back into the real world to validate it, to test it, to conclude on the questions we have posed, and to see if the model is a good model or not. As I said, we will look at 2 situations in this lesson. First, we will collect the data in the classroom. And in the second situation, we will use previously collected data. In both cases, we will 1. Pose some questions. 2. Construct a mathematical model of the situation. And 3. Use the model to answer the questions. Now I'd like to go to our whiteboard in our mathematics laboratory and form some ink blots on paper towel and study the relationship between the number of drops that form the blot and the average diameter of the blot formed. Except we're not really using ink, we're using juice, but that doesn't matter. It's a model. Here we go. This is the paper towel upon which I will drop the liquid. Here we have the input-output table. The input is the number of drops. It is a whole number, n for the natural numbers. Over here, we will put down the data that we will collect, which will represent the average diameter of the blot formed by this many number of drops. So here is the liquid, here is my dropper, and now we have 1, 2, 1, 2, 3, 1, 2, 3, 4, and finally 1, 2, 3, 4, and 5. While the liquid spreads and is absorbed by the paper, I want to explain to you what we're going to do. In each of those circles, or approximate circles, we will measure the diameter. Now we want the average diameter. So really, if we had time, we would take lots of diameters and make the average. We don't have all that time, so we'll take the short diameter and the long one, just from approximation, from what I can see. And we'll have a more or less good measurement. In our first drop, we have 2.2 and 2. The average is 2.1. In the next one, we have about 3 and 2.6, that looks like. Between 2.6 and 3, we have an average of 2.8. In the third one, let's see, a short one would be maybe 3.3, and a long diameter would be about, 3.7. So 3.3 to 3.7 gives an average of about 3.5. This is all in centimeters. In the fourth one, let's take a long diameter here, because it's not perfectly circular. We have about 4.5, and over here we have about 3.7. Between 3.7 and 4.5, halfway between them is about 4.1. And the last one, let's take a long one here, 4.8, and a shorter one, that's about 4.4. Between 4.4 and 4.8, 4.6 is a good number. So here we have the average diameters of these. It's not perfect, but it's good enough. Now I'd like to input those values, the x and the y column, actually you looking at it this way, the x and the y, into our lists L1 and L2, and discover if we have a linear relationship or something that approximates a linear relationship. In the L1 column, we will input the number of drops. So we had 1 drop, 2 drops, 3 drops, 4 drops, and 5 drops in our experiment. In L2, we'll put down the average diameters we computed together: 2.1, 2.8, 3.5, 4.1, and 4.6. Those are on the whiteboard, which are next to me. Now, we'd like to find a relationship between these two. So we want to go to Stat Plot. We want to turn on the plot that will plot L1 and L2, because that's where we put our data. So let's select Plot 1, turn it on. It's now on, and X is the L1 and Y is in L2, so that's correct. We now go to Zoom, and we go down to Zoom Stat. It will plot those points, and this is used in statistics. That's why it's called Zoom Stat. And there are the points. Well, they're very nicely linear. They're actually beautifully linear. Now, this is called a scatter plot in statistics. When we collect data, if we were to trace them, here we have the x-coordinate and the y-coordinate of our first ink blot. 1 drop gave a diameter, or an average diameter, of 2.1 centimeters. The second ink blot, which is here represented by a point, was 2 drops, and it gave an average of 2.8. All the way up to the fifth one up here, we had 5 drops and it gave an average of 4.6. This is actually surprisingly nice and linear. Usually when you collect data, it's not that perfect. Now, how are we going to find the equation of the line that best fits this data? Let me turn the trace off, and now we just have those 5 points. One thing we can do is get an eyeball fit line. It's called an eyeball fit. Here's a piece of spaghetti. I could, for example, decide that my line will go through the first point and the 4th point and leave the 5th one below and the 2 and 3 above. That's probably a pretty good approximation. So you know how to find the slope between 2 points. That's a previous lesson. So you'd find that slope, plug in a point, and you could find the line. Another way would be to take 2 by 2, these 2 points, and then these 2, and then these 2, and then these 2, and find the slope between 2 consecutive points. Then you'd have 1, 2, 3, 4 slopes. You would then find the average. So whatever you do, the more computation you do, the better line you have. So that would be an average or a good fit. First would be the eyeball fit. Then if you took all those averages of the slopes between 2 consecutive points, you'd have a better fit. But there is a best fit line, and that's provided by the calculator. So let's go to calculating regression. That's what we call the regression line, and that's done by the statistics of the computer. We go down to number 5 for linear regression because it looks like it's the line of the form y equals ax plus b. So we select linear regression, and now the calculator is waiting for the data. Well, the x data was in list 1. We put a comma, and the y data was in list 2. And now we push enter, and the calculator gives us the line. This is the slope, the A, 0.63, the B is 1.53, and this is the correlation coefficient. This tells us how good the line fit is. And the closer this number is to 1 when the line increases, and the closer it is to -1 if the line decreases, the better the fit. Well, this is an excellent fit. 0.997 is very close to 1. So now we're going to graph this line. We'll try to remember 0.63 and 1.53. Let's go to y equals 0.63x plus 1.53. No, that's 5.3. That was the A and that was the B. Let's go back and check very quickly if we did it right. A and B, we've got it right. There's a quick way to do that, to bring that equation into this, but I didn't want to confuse you at this point. We're still in the beginning here, so that's good enough. That's ax plus b. Now let's graph this line on top of those points and see what this regression line or best fit line looks like. Well, that's pretty close to what we thought we would do with the spaghetti. We'd said that we'd go from this point to that point, leave these 2 above and that one below. This is pretty close to the spaghetti line. Now, I'm going to delete these and just have the line and zoom out to see where it lives. So let's turn the stat plots off. So we go down to 1. We want to turn it off. And now we go back to graph and we have all the points we want. We're still within the window of our experiment, so if we were to trace and zoom out, let's trace at center the spider here and zoom out around this. We go to zoom, 3 is zoom out, and now we have the line. Let us use this model that gives us on the x-axis the number of drops and on the y-axis the average diameter of the blot formed to answer the following questions. 1. Does the y-intercept make sense in this model? Number 2. What is the diameter of a blot formed by 7 drops? Number 3, how many drops are required to form a blot that would be 10 centimeters in diameter? Again, we're going to answer these questions, solve these equations, by using the graph, by tracing, and using the table of input-output values by using table set and table. So let's answer those 3 questions. First question, does the y-intercept make sense? Let's trace it and go to the y-intercept. And this says that if I have, of course these are decimals, but we're close by. If I have 0 drops, I would have an average diameter of 1.5 centimeters. Well, that's nonsense, because if I have 0 drops, I have no blot at all. So this should be 0. That shows you that when you have a model, we sometimes delete part of it and just use the other part. Here, clearly, we would start at 1, which was the 1 drop, and anything to the left of 1 would be discarded because it would not make sense. All right? That's the answer to the first question. Number 2, what is the diameter of a blot that is 7 drops, or formed by 7 drops? So let's trace and go out to 7. X equals 7 is about there. This is approximate. So this is pretty close to 7. Our answer would be pretty close to 6 centimeters. That's again using this model. And it's logical from the quantities we got up to 5 drops. This is a logical answer. And the third question was, how many drops are required to form a blot that is 10 centimeters? The question now is reversed. We're saying if y is 10 centimeters, how many drops would I need? Well, I think I need to zoom out again, because if I keep on going up, I won't reach 10 in this window. So either I go to window or I zoom out. Let's do zooming out. So I go down to 3. And now you're going to see more of it. If we trace, we now go to 10 centimeters. So there you are. Y equals 10 centimeters corresponds to about 13.5 drops. Now let's answer question number 2 and 3 using the table. So let's look at table set. We asked for 7 drops, so let's start with 6 as the beginning value and increase by 1, because 1 is 1 drop difference between one and the next. Okay, so we start at 6 drops and we're going to read it 7, 8, 9 increments of 1. So we now look at the table, and at 6 drops we have 5.31, at 7 drops we have 5.94. That's exactly what we read on the graph. So the second question said, what would be the average diameter if I drop 7 drops? The third question said, if my diameter is 10, so now if we go in this column, and we go down to 10, now 10 is not here, it would be in between, and we said it would be between 13 and 14 drops, which again is good enough. We could refine this, and we could start at 13, go back to table set, start at 13, and then make increments of 0.1. We would be refining our table, we then go back to table, and now you would be able to find 10 a bit better, and here we are. Actually, this one is probably better, 10.035, very close to 10, and it's 13.5. And again, you could keep on refining this as much as you wanted. So, we found a model that was a line, and we learned something that is true of very many models, and that is sometimes the entire equation is not our model, but just part of it. We saw that we had to delete the part from the left of 1 because we didn't have an intercept of 0, which logically we should have had. And then you might even say, well, if I get all the way up there where I have 20 or 15 drops, it might not continue in a line, because maybe if you drop a lot of drops in the same point, you might perforate the paper and it won't spread as evenly as the first few blots. So those are the type of things you learn from experience. Now we're ready for problem number 2. In problem number 2, we're also doing a modeling problem, but we're not going to collect the data in our laboratory. My data is already stored into my computer, and here's the story that goes with it. Christopher was interested in buying a car. He couldn't afford a new car, so he looked up the classified ads, and he found cars of the same make, model, and year that he was interested in, and he jotted down the mileage and the prices to try to find a relationship between how much would a used car cost given so many miles on the car. So then he can then predict if he can afford a relatively new or a very old car, 1 year, 2 years, 3 years, 50,000 miles, or whatever. So let's see what data he collected from the newspaper. This is a great problem that you could do selecting a car that you're interested in. Under L5, you have the mileage of the used cars that Christopher found in the newspaper. And in the right column, L6, you have their corresponding prices. So at 16,500 miles, the cost was $12,600. If I go to the top of the list, here we have 2,000 miles, and that cost $16,300. We notice that as the mileage increases, the price decreases. That's logical. It will be a line that falls or drops or has a negative slope. Let's plot these points using stat plot. We have our data in L5 and L6, so let's turn on plot 3. We turn it on. We make sure that our X values or input are in L5, Y values or output are in L6. We now go to zoom. We go down to 9, which is zoom stat, which we visited before, and there are our points. This time the points are not as perfectly aligned as last time, but still you could use a piece of spaghetti here and find an eyeball fit. For example, that would be one that would be pretty interesting. You could do that one by hand because you have 1 point above and 1 point below, so they kind of average out. That would be a good one. Another way of doing that, to find a line that would be a good fit, would be finding the slope between 2 consecutive points, and then maybe between those 2 points, and then maybe between those 2 points. Once you find many slopes, then you would find the average of those slopes, and that would be a powerful slope. That would be another good fit. But we're going to use the best fit, or the regression line, provided to us by the statistical program inside our calculator. So let's do what we did before. We go to statistics, we go to calculate, and we suspect it's a linear function, y equals ax plus b, where a is negative because the slope comes downhill. So we select 5, and now we need to place the lists of the data where it's stored. L5 contains the x, comma, and L6 contains the y. There is our line. Y equals ax plus b is the general form. The slope is indeed negative 2 point, it's a negative slope. Here it's negative 0.2527, etc. The b is 17,057, and the regression correlation is minus 0.987. It's still relatively close to -1, so it's a very good fit. It's not as close as last time. We had a 0.99. Again, the negative is because it's a negative slope. So let's put this a and b into our y equals. So let's remember negative 0.25, that's good enough, and 1757. We'll clear that one out. We have minus 0.25x plus $17,057. Let's now graph this line and see how well it fits the data. Well, that's pretty good. Again, notice that you have 1, 2 above, 1, 2, 3 below. This is more or less above, so it made an average. Let's use this model, now that we have a mathematical model, to answer the following questions. Number 1, Christopher's friend has 8,000 miles on the same type of car. What is it worth? 2. Christopher wants to spend $10,000, no more than that. What mileage might he get for that price? 3. Suppose a similar car has 50,000 miles on it. What might it sell for? And finally, what is the meaning of the x and y intercepts? So back to the graphing calculator to answer these 4 questions. Let us turn off stat plot, so that's 4, and let us change the window so we can see the axes. Let's go from 0 to 70,000, and for the y, negative 1,000 to see the horizontal axis to 18,000. Now we have the graph. We see the intersection with the 2 axes, and we can answer the question. First one, at 8,000 miles, what is it worth? 8,000 miles, we need to look for 8,000 in the x value. That's 9, 8, there you are. Approximately 8,000 we are, so about $15,000 would be the cost. Next question, $10,000. What might the mileage be? We need to go to 10,000 now in the y value. Remember, the y is the cost. So here's 10,000. This is close enough. The mileage would be about 27,000. Third question, at 50,000 miles, that means we need to go all the way down to 50,000 for x. Here it is, about. What might it sell for? Very little, about 4,000 some odd dollars. The last question says, what's the meaning of the intercepts? Well, if I'm all the way down here, if I come down to y equals 0, that means that my cost is 0. That says that after about 67,000 miles, the book is no longer going to be listed even in the blue book. The car, rather, won't be listed in the blue book because it's worth nothing anymore. All the way up here would be the new price. If I go up to the top, when x is 0, meaning when there is no mileage on the car, so we come all the way down to x equals 0, that might give you, there it is, the value of the new car, $17,000 new. To reiterate the final result we just found, when x equals 0, no mileage, the cost of the new car would be $17,057. That's probably reasonable. In the past several lessons, 5 through 9, we've been looking at linear functions of the form y equals ax plus b, or f of x equals ax plus b. That's the same thing. And we've studied these functions either from a problem situation, or from a graph, or from a table of input-output values, and so on. In all those cases, the line was exact. In this case, in mathematical modeling, we've seen that there is no exact answer. The best we can do is come up with the best fit line. But there's not one right answer. Let us recap what we've just done. 1, we collected data from the real world. 2, we understood this data. 3, we organized and represented the data, in several forms actually. And 4, we analyzed the data, answered questions, and made some predictions. How were we able to accomplish this? We constructed a mathematical model. In this case, it was a linear model of the form f of x equals ax plus b. The model was not exact, but it was a line of good fit. And finally, with the aid of technology, we actually were able to find the line of best fit. To find that line of best fit, we needed the help of the calculator. Had we not had the mathematical technology, we would not have been able to do the mathematical modeling exploration of today. The process that the calculator or computer uses to give us this best fit curve or line is called linear regression, or other forms of regression analysis. That process is very complicated, very difficult, and very advanced, but it's not something you shouldn't try to do in later years, when you know more mathematics and when you have more skills and concepts. So look out for that in future years. In the meantime, use your calculator.